people are, see what they look like. I want this. Am I really gonna be the only one here? I'll give it a couple more minutes. I have a toothache. It sucks. Alright, we're gonna start in 3 minutes. Hey, Dad.
Hello.
Hey, how's it going?
Good. How are you?
Pretty good. How about yourself?
All right.
I think you're like really the only one here right now.
Yeah, I definitely am.
Okay. Well, we're also
I think it,
streaming live right now. It's in the announcements, the link as well.
yeah, I
Uh,
saw that.
thing is it's the I wanted to I wanted to do some video conferencing because apparently screen sharing doesn't work in Discord, and this has a delay. You know, the YouTube broadcast. So I was trying to do like live share screen somehow. And I was thinking of doing Google Hangouts for some reason. I'm trying to figure that out. Problem is that it's showing both of my screens. It sucks.
Hmm.
I have a dual monitor.
No, I was just wondering. So is it the Google Hangouts or is it the YouTube or?
Oh
Because
no.
I
Mhm.
see the YouTube.
Yeah, the
It's
YouTube.
live.
Yeah, YouTube is good. I'm just saying, Google Hangouts suck. Because
Oh yeah, yeah, yeah.
it's showing double screens. I'll just share the link with you, anyways.
No, I already have it.
Oh, you have the Google Hangouts.
Yeah, yeah.
Oh, okay. Um, are you in it already? In Google Hangout?
I was, but then I left because it says I was the only person there.
Oh yeah, I'm here now.
Oh.
I hate it because Linux, uh, Google Hangouts is not good with Linux. Not very well. I have Linux.
Oh, the only problem is that Google Hangouts is I'm on my phone for Discord.
Oh, okay.
Yeah. Oh, yeah, it's like video Hangouts. I see.
Yeah. 'Cause I wanted to share screen live so we can like look at our screen and share
Oh, I
see
see.
what's up. But the problem is with Google Hangouts, it has because I have two monitors. You know what? I could just do it this way. This is so stupid. I hate it though. I'm just gonna disable one. Okay. Whoops. Can you see it now? The Google Hangouts as well?
Huh? Oh, on the same screen? Yeah, I
Uh,
see the infinite. Oh,
okay.
I closed Google Hangouts.
Oh, you've closed Google Hangouts?
Yeah, because I'm not, don't really have anything to share.
Oh, okay. No, well,
Yeah.
okay. Well, if you want to just look at my, I guess my YouTube stream, then that's
Yeah, yeah,
okay.
yeah. That's,
It's a big
yeah.
delay though. So it'll be like kind of weird, like, cause when I'm talking, you'll see like some sort of delay lag, like of what you're seeing actually. You know what I'm saying? Does that make sense?
Yeah, yeah. I had myself muted. I was just talking to myself.
Okay. All right. I guess we should start. You're basically the only one. I'm not sure why you're the only one. A lot of other people should have come here, but it's okay. Uh, one sec.
Alright,
I
that's
like
cool.
this cheesy desktop background. It actually works for me. I don't know why. All right. So, I wrote notes, and basically, welcome to chapter 2 and 3 of ISLR. And so, so this is actually just the start of a new, like we're starting all over again. We had our study group a while ago, like a long time ago, and it's just a lot of mishaps. We were trying to debate like what kind of resources that we should study off of, and a lot like just basically we first wanted to do the Google Developers Bootcamp, but it was just not thorough enough when we were uh, when we were trying to study it, and so we came to this conclusion doing ISLR, and this book is actually very recommended to a lot of schools and stuff like that. In fact, I used this book as in one of my classes in my school a year ago, and so I'm just re-studying all this stuff and stuff like that. So I guess we just agreed upon like learning this book and stuff like that. But anyways, um, so we're gonna cover briefly on chapter 2 for maybe like the first 15 minutes because This is actually really foundational, and we just have to be on the right page of sharing our jargon and stuff like that. Um, so, so going on, delving into chapter 2, it talks about, first of all, there's two different types of um, learning, superficial and unsuperficial. And superficial studying basically means is that you have a data set and you have a column where you have all these other columns that probably makes up to that one single column. So let's say like housing prices, right? So let's say you have a data set of housing prices and all, like, you have all these columns, and like let's say the housing's area, the size, like the location, those are all just the columns, right? But the housing price column is actually the response variable. And that's what superficial learning means. Superficial learning is that you're actually feeding into the data the response variable, which is the
Wait. You're saying superficial?
or not supervised. Sorry.
Yeah. I was wondering.
Supervised. Sorry, supervised learning. I don't know why I said superficial. My mind is going everywhere. Um, supervised
Yeah.
learning.
Yeah, you have the predictor in the you have the answer in
Yep.
your data set.
Exactly. Supervised learning is basically a learning that you are trying to predict something. So based upon that response variable, based upon that housing sales price. Unsupervised learning is just basically trying to study the relationship between two variables, or understand, or like trying to find out what kind of any type of relationships, whether if there's a correlation between two columns in the data set or 2 to 3 columns in the data set, but basically you're trying to find out. You're not trying to predict anything. You're just trying to know what's going on with the data right now, and you're just trying to find out what the relationship is between one variable with the next variable. Going a step back, we're gonna have to kind of redefine some of the terminology. Variables. What I mean by variables is dependent variables or features, aka features. And those are columns on the data set that are different features that make up a certain data set. And the independent variable in a supervised learning is your, I guess, your predictor type of column, which is the housing sales data. So features, aka dependent variables, and response variable, which is the housing sales price. How much more minutes do we have left in chapter 2 already? That's okay.
In the book, don't they call the attribute or the feature vectors the columns themselves the predictors?
No, the features is basically the columns that are like TV,
Yeah.
radio, newspaper, or something like that.
Yeah, but I think in the book though they call them predictors for some weird
reason.
Yeah,
Exactly. That's another terminology. Predictors. Those are that. You're right. Predictors.
It's very weird.
There's a lot of.
I've only seen it in this book. I've only seen that in this book.
Yeah. True. There's predictors. There's dependent variables. There's features. There's those are all the same. They're all the same.
Yeah, sometimes called attributes as well.
Yeah. Statistics side, we have to say dependent variables and independent variables. That's the statistics world terminology. In Google Developers Bootcamp and all that other the technological side, they call them features and labels. Labels is the independent variable. Get it? It's AKA independent variable. So
Yeah.
based upon which industry that you're at, in the statistics world or in the technological world, they all mean the same thing. You just have different terminology for it. So, um, so that being said, let's see here. What else do we have to go through? Let me check. Give me a moment. Yeah, so I only have like 10 minutes of talking about chapter 2, but this one is actually very important. There's two main reasons we wish to estimate: the prediction and inference. So prediction is definitely straightforward. We just talked about it. We're just predicting the data based upon the response variable. Inference, however, do you know what inference is?
Yeah.
So it's just inference basically means that you inference basically means that you're actually studying the relationship between the two relationship between the data. Let's see here. You're interested in how y is affected as x, as how all the features change. Where in this book, y represents um, the sales data or the response variable, and you're interested in how y is affected as all the other columns in the data set, x1 through xi, and how it changes. Also, x also means features. So our goal is not necessarily to predict y or response variable, aka labels. But we're actually just interested in how they're associated with the response. So some of the good examples would be like, what is the relationship between the response and the predictor? So that's what inference means. Can the relationship between the response variable and each predictor be summarized, or is the relationship more complicated? You know, and that's what inference means. And then like that's basically derived off of inferential statistics, and that's just a whole different. It's not different, but it's basically that whole world right there. So, and one last concept that I want to cover is parametric and non-parametric methods. Parametric basically is an approach to how you're researching your data set. So parametric basically means that you're creating an assumptions, multiple assumptions in your data. So the reason why this is very important is that let's say, for example, we're assuming that this data set is linear, you know. So f of x, f of x equals all these parameters times x1 plus parameter 2 times x2 plus blah blah blah, all the way up to whatever features that you have, and we assume that the function is linear. The reason why we want to assume we want to go for a parametric route is because if we once we like identify and assume certain data sets, we can actually pinpoint which types of algorithm that we could use, right? Which appropriate algorithm that we could use. So basically linear regression, we could do that. We could also do smoothing spline, apparently what's in the book, even though that is a very flexible method. And
Did you mute yourself?
no?
Oh, never mind. I muted my earphones.
Oh. After the model is selected and parametric also means is the process of training and testing the data as well on the fit of the algorithm.
You should do that on all types of, so parametric or non-parametric. You should definitely do the testing.
Let's see here. So yeah, that's a very good question. Or interesting thing, because when you're in a non parametric, you don't make explicit assumptions. You're just basically treating everything generic. You don't have.
Uh, there's always some assumptions, but yeah, in general, I mean, you can consider it that way.
Okay, according to this book, you don't make explicit assumptions though. So uh, you seek to estimate a. Uh, so you try to find a non-parametric like algorithm that could be like
Mm-hmm.
generic for that could be generic for almost most of the appropriate data sets possible. But the disadvantage of that is that you're uh, first of all, it might be computationally expensive. But the second problem is that since they don't reduce the problem of estimating um, a very large number of observations, data basically is required in order to obtain an accurate outcome for non-parametric. So, or yeah, for non-parametric approaches. So, but then fortunately for linear regression on chapter 3, this is all going to be parametric because we're already assuming it's linear, and we're actually just going to do the ordinary least squares approach algorithm, which is a parametric approach. Uh, Non-parametric is just one of those generic algorithms, statistical methods that we could do, but that's like we're not going to cover that right now. Um, okay, that was already 15 minutes, but like just give me one more minute. Uh, there's a trade-off between prediction accuracy and model interpretability. Um, all in all, linear regression is not a flexible approach. What I mean by flexible is that you have so many assumptions that the data set has to be linear. So it's pretty much inflexible. The inflexible
Uh, the
approach.
the data set doesn't have to be linear. So the reason that they call it linear regression is that the coefficients you learn are linear. There's an example, I think, in chapter 3 where they do polynomial linear regression.
Oh, nice. Uh, According to this book, it's just that the actual algorithm, linear regression, is a very inflexible approach, but the interpretability is actually really good. So if you're working for a company and your manager is saying, "Yo, uh, so do you know how much this housing sales price costs in this area?" And you'd be like, "Yeah, like with just 5% of or 95% confidence, we're doing it this way. It's this much. Blah 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 blah. But that's only just for like I guess like um for data sets that we know that we're gonna go through that approach. But if there's a more complicated data set, then we have to go for maybe uh, like a more flexible approach where if the line fits the data, it doesn't fit the data, so we need to have another algorithm. But it might be a little bit more complicated to interpret. So there's a different trade-off between that, right? And so
Yeah.
let's see here. It is on page 24 at the bottom.
All right. 24.
Yeah.
Hmm.
It's just too
See
much
if I can...
block of text though.
Oh man, the PDF is not 1-to-1.
I use
Crap.
continuous like scrolling.
Well, I typed in 24, and it took me to page 9.
Oh.
Oh, here we go. Oh yeah, this.
Yeah.
Oh yeah, this stuff. Yeah, I know what this is.
Yeah.
Yeah, this is talking about the complexity of your model. The more complex it is, the harder it is to describe. So, for instance,
Yep.
if you have like a neural network, or if you do boosting or something like that, you just have too many moving parts. And you're just like, well, I don't know what it is.
Yeah.
Actually, that's not true. For neural networks, you can actually extract information out of the nodes themselves. You can find examples online where they learn cats, and then when you print out like what the nodes look like as a bitmap, it
Mm-hmm.
kind of looks like a cat, which is pretty neat.
That's awesome, though. Interesting. So, I guess that's pretty much it. I don't want to get any more. There's also this thing called bias and variance. Uh,
That's a little technical.
yeah, that's a little bit more technical. If you have too much variance, like if you have one algorithm and you've built out your model in your coding using scikit-learn or whatever R or whatever, but then you get another data set, but then the outcome is not expected. That means that you just have high variability in your algorithm. And your
Yeah.
biasness is basically something that you can't really fix. You just have a lot of error terms, whether if someone actually manually entered data, and that's prone to a lot of errors. And so,
The bias is related to the complexity of your model. So the error is if you look at the formula, it's on page.
oh yeah,
Let
yeah,
me
that's
get to
true.
it. 34. There's the variance at the end, the e. That's the thing. What do they call that? They call that the
Error term.
no, no, no. There's like a term. There's a term between the ones you can control and then the ones you can't control. I'm trying to remember what it's called.
Oh,
Yeah.
yeah, 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 yeah.
Too many terms. Yeah. Yeah. Anyways, yeah. So there's parts you can control, which
Yes.
they're based on the model, and there's the parts you can't control, such as the error.
Yeah. Oh
And
yeah.
I just can't remember.
Uh, I did read that, and I totally forgot what it was. Man, man, I wish we could be more thorough, but I feel like I have to take 2 weeks of studying this instead of just 1 week. I studied so hard on this too, like 3-4 hours a day, and I still can't get everything right.
Well, the thing is, you don't need to memorize it all.
That's true. And so basically, bias refers to the error that is introduced by approximating a real
Uh,
life problem, is what it's saying, which can be
uh,
extremely complicated by a much simpler model.
yeah, that's what it is. It's related to the model you choose.
Yeah. So
Yeah.
it could be like an error from erroneous assumptions. High bias can cause an algorithm to miss the relevant relations between features and targets.
Yeah, if
Low
your model is
levels.
too simple.
Yeah, if your model is too simple, for sure. So that could be like a high bias in your data. Variance is what I just said before. Oh, well, anyways, all right, chapter 3. We went
Yeah.
too long on chapter 2. But we did have to. That is actually very foundational, I think, in my opinion. I don't know.
Hmm.
All right, simple linear relationship, simple linear regression. Um, can you name what the equation looks like? It's so simple.
For lim- Oh, you mean the linear regression model?
Yeah, just one variable linear regression model. What's
Oh
that?
yeah, one variable is just cx plus the
Yep.
I always say b for bias, um, but they call it, I think, b0 and b1.
Yep. Exactly. And so B0 is the intercept.
Yeah.
B1 is the slope. Uh, X is your features. So let's say newspaper or radio or something like that in your data set. Um,
You'll see in some books that they call the intercept also the bias, which is a little weird, but
yeah, I read that too, so that made me like throw off so bad. I hate this so much. But you're
yeah.
right. I did read that part too. Let me go down to chapter 3 for a sec. This might take a little longer than 1 hour that I was hoping for. Um, so the concept of B0 and B1, they represent the internet slope. I just said that. Um, They are also known as coefficients and a parameter, aka
Yeah.
coefficients, aka parameter. So many terms that mean the same damn thing. Y hat, B0 hat, and B1 hat are the prediction from the algorithm that we've created. Is the basically the output. The predict Y hat is the prediction.
Yeah, the prediction. It's the
Yep.
prediction.
Yeah. Okay. Next. So now we need to estimate the coefficients. So, our goal is to obtain B0 and B1 such that the linear model fits the data well. So, can you explain that a little bit better? Because I'm trying to figure this shit out a little bit harder.
All right. So which one are you looking at?
Okay, so go to page 61.
All right.
Do you remember
61.
It's really easy.
Here we go. Yeah. What about it? Are you talking about estimating the coefficients?
Yep.
Pretty much they just skip a bunch of stuff and just say here's the answer.
Basically, estimating the coefficients is what in the book they're just saying that we need to find a line that fits all these, a linear line that tries to fit all the data points into that linear line as best as possible by minimizing the starts with an R.
Distance between the
residual
errors.
Yeah.
Errors. Yeah, but it's better to think about it like you want to minimize the distance between the lines and all the points added up.
Yep, exactly. That's what I was gonna say, anyways. Just joking, not joking. But that's also called a residual sum of squares.
Yeah, you only hear that in statistics, I think.
Yeah, it's definitely a very statistics-heavy terminology. Yeah, if you want to do like a technical interview in a company, you probably just say you just add up all the distance between the points in the line. You basically calculate the residual sum of squares, which is the thing that we just said, and using the least squares approach, you want to minimize it somehow. Oh my god. And this part just threw me off so much. If you go to like page 62 all the way to 63, like they're just basically, you basically have to calculate in a very mathy way how they do it.
Oh yeah.
All this is irrelevant because we're actually just going to code it, and it's just going to calculate for you anyways, the minimum. So
sure, as long as you have a single variable.
Yeah, exactly. Oh yeah, we are still only talking about the single linear regression.
Yeah.
Okay, so the next step after that, once we apply the linear regression or the least errors, is the least sum squared.
Least squares coefficient estimates.
Yep, and then we need to assess just the least squares approach, I guess. We just need to apply that one. We just need to apply that line first, and then after that, we assess the accuracy of the coefficient estimates. That's step 2. And let me... They do it very statistics heavy wise. Man.
What are you looking at?
Oh, we're page 63 in the middle. But I'm looking at my notes too at the same time. It's just so very statisticsy.
It's hard to follow what you're doing.
Oh, sorry.
What you're looking at is definitely, it's on page 65.
Yeah, 65,
the
66.
What is that, the standard error?
Yeah, the standard error. The standard error of the predicted mean.
you know,
or
it's a little
mu.
weird. They actually square it.
Hmm. I mean, I get so lost because I'm not a huge statistics heavy type of guy.
Yeah.
But you, if you read that one, there, I posted the video or the video lectures of this book too, and they kind of say it too at the same time. But it's still very statisticsy. It's like
Yeah.
and then like it doesn't really matter, especially when you're coding, because you have in scikit-learn or R, you already have a method when you're writing your code, and it does it for you anyways. So it already uh, calculates the the algorithm with all the
I mean,
false
this is all
scenarios
just,
and stuff like
yeah,
that.
this is just theoretical background and stuff like that.
Yeah. So, but then the next step is assessing the accuracy of the model. And did you read about the residual standard errors and the R squared and stuff like that?
Yeah.
It's on page the bottom of page 68 and 69. Um, and so that's the third step. This one is actually just you're assessing the accuracy of your line fit using two different methods: the residual standard error and the R squared statistics. This is actually very important, I think, because that's when you actually have to manually program this as well. I think, or not. Actually, there's another I think method for it depending on which programming language that you're using. In scikit-learn, I think there's this thing called RSE, or maybe not.
Yeah.
I'm not sure. But in R,
It's,
there's something else.
it's residual standard error or something like that.
It is. It's the residual standard error, and basically what this is that um, the residual standard error is an estimate of the standard deviation of the error terms. So roughly speaking, it's the average amount that the response will deviate from the true regression line. So and so if the RSE equals so let's say for example 3.26, I'm reading off the book now. The actual sales in the market deviate from the true regression line by approximately 3,260 units on average. So it's basically measuring what the difference between your line and then the true regression line, the hypothetical true
Yeah.
regression line, and you're just basically like calculating the range of it, like on the range of the average outcome. Does that make sense?
It's this. It's the standard deviation of your error.
Yeah, basically.
No, that's exactly what the book says.
Oh, is that? Is it?
Yeah,
Okay.
yeah. It's the estimation of the standard deviation of your error. So you said pretty much the same thing.
Yeah. It's considered um the lack of fit type of. So that's how you assess it, kind of. That's residual standard error. In scikit-learn coding, you're gonna have to do that too. Um, um, you're gonna code that. And there's another approach called the R squared statistic. This is way more manual. Um, to be honest, it's actually very computational heavy, but it's also super easy to interpret. So basically, you have your total sum of squares minus your residual sum of squares. So your total sum of squares, what that basically means is all your data. Uh, so your all your all your response variables minus your uh, predicted response variables squared, and you minus that by your residual sum of squares, which is the error distance, the mean, the sum of the error distance of your line fit, divided by your total sum of squares. It's really it's just basic algebra.
Yeah.
And basically, if r squared is close to 1, um, it has a very small residual error. If r squared is close to 0, so the outcome is either 0 to 1. So it's going to be decimal. It's going to be a decimal answer, r squared. So if it's closer to 1, it has a small residual error. If it's closer to 0, like 0.001, that's a serious problem, because then your line of fit is actually completely bad, you know?
Yeah.
So that's all you need to know. That's what r squared basically. It's just an ad hoc, like just regular algebra type of calculation. Um, yeah, that calculates basically all your sum of squares. Divide by your, or minus your residual sum of squares. Divide by your total sum of squares. Um, let's see here. And now I think that's it. Then I was reading the next section. It was talking about like, oh yeah, the next section is basically now multiple linear regression. Give me a moment. My brain hurts.
You skipped out on correlation.
Yeah, I didn't know anything about it, and I was too bored.
The correlation will give you information on the relationship between the input and your output. So, for instance, you can say it's either positively related, negatively related, or zero, which means not really related. So it's talking about the linear relationship of the two.
Oh, interesting.
There's actually a giant graph somewhere on this stupid book. Let me find it real quick. Oh yeah, there's a on page 83. You can kind of usually they look something like that.
Let's
Usually,
see here.
well, maybe not exactly like that, but pretty close.
Cool. Oh
So it
yeah,
looks
this
like
thing. Yeah, I saw this. Yeah.
yeah, something like this. Usually it doesn't have this weird stuff. Usually correlation graphs will look like the bottom right, those two, or some type of weird. Everything's connected. It doesn't look like the. I don't know what the hell how you even describe these ones that have just a bunch of lines straight left and right or up and down.
Mm-hmm.
It looks more like the ones where everything's kind of clustered together in some weird um, order. You can definitely tell there's sometimes a relationship. Unless there's not a relationship, then you're kind of screwed.
Yeah. And I think this
Yeah.
is another good indicator of which type of dependent variables are relevant to your multi or
Yeah, yeah.
for multilinear regression as well.
Yeah, you can tell which variables, yeah, are the most important.
Yep,
In some ways.
exactly. Which is a good segue because we're gonna go to multilinear regression now. Let me scroll back up. Multilinear regression. It's the same thing except now that we have more than just one variable. The intercept is still b0, but then you have multiple slopes that make up for the line of fit that you need to work on using the ordinary least squares approach. So basically, in the real world, you can't just only have one variable. That's stupid. I mean, the world is too complicated for that. And so now you have multiples, and we need to estimate the regression coefficients. It's almost the same way as the one we talked about before, but this time it goes. So it's basically the residual sum of squares is still basically the sum of all the response variables, the difference between the response variables, and the predicted variables squared. Let's see
I like how they just skip out on the solution. You just say your software package will have it.
Yeah.
That's kind of sad.
But you know what? If you go to page 75, there's these 4 questions that are actually kind of interesting to me.
Yeah.
These 4 questions is basically like your coding pseudocode steps. Kind of. Or your way to find out and stuff. Let's see here. I wrote notes on this. Okay. Statistics wise, okay, here's what we're gonna do. So because this is multiple linear regression, you want to know where the step 1. You want to know the relationship between the response and the predictors. So in statistics, we do these things called the null hypothesis and the alternative hypothesis. The null hypothesis is that we're assuming that all the features in our data set has no relationship between the predictor or the response variable. But the alternative is that at least one feature has a relationship between that and the response variable. So in order for us to do that in statistics, we calculate the F statistic. Mind you, if you're just only want to do programming and stuff like that and just want to calculate this, you don't really have to know all this stuff. But in statistics, like all that stuff is behind the scenes. So if you come up with there's one algorithm in scikit-learn, it shows up your F statistics, and so your F statistics is basically saying that like if it's a value close to 1, basically, then there may be no relationship between any of all the it's not statistically sufficient to conclude that all the predictors have any relationship between the response variable. But if it's greater than 1, actually everything is going to be greater than 1, but if it's going to be like significantly greater than 1, like 300, if the outcome is like 300 from the F statistics calculation, then there's definitely obviously at least one is related to the response variable. Get it?
Oh yeah.
But the book actually says, how large does F statistics need to be before we can reject the null and conclude that there is a relationship? So in other words, how large does the outcome of the F statistics need to be before we need to reject before we conclude that there is no relationship, you know? Mm-hmm. So a good tip is in the book is that if the number of the data points is large, and it's still only a little larger than 1, only a little bit. That might still be, there might still be a relationship between the dependent variables and the independent variable. However, if a larger F statistics need is to reject If the number of data points is small, then we definitely need, like, in your subjective opinion, like a much larger score in your app statistics, a lot more, because we just don't have enough data, and you know, just the probability of having it would have a relationship, you know. If it's
Oh yeah.
like 5 versus like 200, obviously there is a relationship. 205 is just like nothing, you know. Makes sense.
Oh yeah, yeah.
Okay, now here's the fun part. Now we need to find out what are the most important variables or the predictors of them in your multilinear regression. Uh, so in this book, they just briefly mentioned if the number of predictors, the number of columns in your data set is actually kind of small, like less than 5 maybe, you try these like different like methods like the Mallow CP, AIC, the Akiki information criterion, the Bayesian info criterion, the adjusted R squared, and we're probably going to cover that in chapter 6 or something like that. But that's what they just briefly said that. However, if the number of your data set, your number of columns is large, and you want to find out which variables or which predictors are your most important, you use either the forward selection, the backward selection, or the mixed selection.
Yeah.
And in scikit-learn or in R programming language, there is a algorithm to do forward and backwards. There's a argument that you can put in, type in forward or backward, something like that, to do the forward selection, backward selection, if you call out a method in that programming. So forward selection is that you just begin with a null model, and then you just incrementally add p, and then it calculates. Okay, is this like? Wait, hold on one sec. Let me say this right. Where am I? I need my notes. Okay. So basically, forward selection is that you begin with nothing, no predictors. You just have a null model, and then one by one, you add in your predictors. That results in the lowest residual sum of squares, the lowest error distance between the line and the data points, and then you just keep adding onto it more and more until you finish up with all your columns or your predictors. Backward selection is basically the opposite. You first start out with all of it, and then you just eliminate it by one. And then your mixed selection is kind of a confusing way of going forward and backward at the same time, you know?
Yeah.
But
except you start out with nothing.
you start off with nothing in mixed selection?
Yeah. There's a caveat in the book that if your n, I think, is less than p, you can only do forward selection and not backward selection.
Okay. And then yeah, that's basically it. That's how you. So in chapter 6, there's a more deeper method. You'd have to find your like your VIF, your what's it called, your correlations, where you don't want to have redundant p predictors that mean the same thing into your algorithm, you know, and all that stuff. But that's in chapter 6.
Yeah.
And we can definitely.
Yeah, you find a relationship between your two.
Yep.
Predictors, and there's no need to have predictors that predict, have the same information.
Exactly.
They call this dimensionality reduction in more machine learning books.
That's what they're saying here too on page. It's called variable selection in variable selection. It's called variable selection. I know. wrote that here somewhere.
That's all right.
Yeah, whatever. I'm wasting time right now. Anyways, so the next step after that, after you figure out what your predictors are, then we do the model fit, which is basically your same RSC or R squared. I know I'm having a really tough time explaining what those are. I guess we did go over that earlier. But basically, you just code it, and then it'll just say the answer.
They just correlate to the error of your model.
Yeah. And then after your model fit, man, the whole model
Hopefully.
fit, there was like, what, 3 pages of reading that crap? Anyways.
You mean getting the coefficients?
Oh no, like read page 79, 80, and 81. It's just all about model fitting. Like using RSC or R squared.
Oh yeah, this stuff.
Yeah. And then the last step is predictions. Then once you have a really good, decent RSC and you've evaluated to having a decent algorithm, then we can just apply. In the real world, you want to apply it to a training data. And this is how far I've studied, basically. So once you do the so prediction is basically you're just applying it now to your training data.
Yeah.
And then
After
you're predicting it.
Yeah. The next section is just turning some considerations. So, for instance, qualitative predictors. You pretty much just take your qualitative values and convert them into numerical values.
Uh-huh.
And then, what is this? Predictors with only 2 levels. Yeah.
Yeah. I studied so hard this week on this whole thing. I allocated way too much time on reading chapter 2 more than chapter 3. I know I didn't even read all of chapter 3 yet. So, like, I think this is, you know that qualitative predictors that you're talking about?
Yeah, yeah.
That's like the qualitative stuff, and then you're trying to change it to a number. That's what you just said.
Yeah.
Okay.
On page, so one of the important things that for some reason is really tiny, it's on the bottom of page 90. It's called nonlinear relationships. It's where you turn your data into other types of models. So, for instance, this is still linear regression, if you want to call it that.
Right.
But you take your data and you turn it into linearize it. That's pretty much what you're trying to do.
Interesting. Wait, hold on. Let me see. I'm gonna write that down. I'm writing notes right now. Let's see, how much is this going for already? Oh, we just passed 1 hour. Or actually 50 minutes. Okay. Yeah, that's good.
Yeah.
I was actually I was scrolling down this chapter and I was looking at this subheader, nonlinear relationships. And yeah, I really wanted to read it, but I was pressed for time and then later down the chapter, there's all these potential problems that you have to look at, collinearity, outliers, all that other stuff.
Oh yeah.
And then it talks about each of those things. And then page 102 is the real world stuff. It's like just a summation of what you're doing applying to the real world.
Yeah, the boring stuff.
I think to me is the most fun stuff because I'm a more practical guy. I can't learn by
Mm.
like studying concepts. So if I have like a real world application example, then I would know exactly how to approach it in other data sets or something. You
Yeah.
know, which is really important. And then 3.5 page 104 in the middle bottom talks about K and N with
Yeah.
comparison to linear. I didn't get this far at all. I don't know I don't know what this is at all. And after that is your end of the chapter, basically. Um,
I think they talk about K-nearest neighbor in chapter 2, don't they? Or chapter 1.
they do a chapter 2, I think. Is it chapter 1? I didn't read chapter 1.
It's somewhere. I remember reading it.
I did not do any coding this week. I was so busy this week. It was insane. I'm gonna do some coding, linear regression. Um, so the people who are actually listening, I want you guys to find a data set that has regression or that has quantitative data points and apply linear regression and share the code with us. But I guess that's it for the day.
All right.
Just to conclude, here's a summary. When you're applying linear regression, number one, for multiple linear regression, try to find if there is a relationship between the independent and dependent using the F statistics. Number two, find if create the line, basically create that algorithm. Number three, assess it using RSC and R squared, and then you can apply it. The code itself is actually super simple, but the statistics behind it is so complicated. And yeah, that's it. I mean, do you have any questions? Hello?
Oh no, I'm good. I'm good.
Okay. I think for next week, we're gonna. This was a huge reading. I mean, we're gonna continue chapter 3 a little bit, like the one that we've cut off, and then read chapter 6, because that actually talks about the ridge regression stuff, like regularizing linear regression, regularization and stuff like that, which is very important because if you're gonna go in a technical interview and try to get a job in data science and stuff like that, they're probably gonna ask you in a technical interview, hey, what does regularization mean? I can't even say that word right, and all that stuff. Um, so be prepared for that, and yeah, learn about scikit-learn. And actually, it's very cool because in this website that I posted in Padlet, it already does tell you about ordinary least squares approach and stuff like that. Yeah. So just go to Padlet. Just look at the ordinary least squares. The code. Really simple. It talks about also later down. It talks about ridge regression, which is basically what's going to be covered in chapter 6 in the ISLR book. And the lasso. These are different regularization stuff. I don't know what regularization means, so I'm just going to say stuff. Maybe it's a method approach or a method or something.
Oh, from what I recall, regularization is to keep your model simple.
Oh, okay.
So in your error function, you try and compute the complexity of your model, and it adds to the error as the more complex you get, so that it'll keep your model simple, not too complicated. So for instance, it's trying to reduce um, oh crap, what's the right term? It's pretty much trying to make it so that you don't learn a model that's identical to your training data.
Okay.
I can't remember. Yeah, it's trying to keep your model general instead of more specific.
Okay.
I can't remember the term off the top of my head that is trying to reduce.
That's cool. Um, yeah, that's actually good. Yeah, go to that one link that I shared in the Padlet. It'll talk about that stuff, the ridge regression and stuff like that. I'm gonna do that next week. Uh, so let's see here. So I have a question, dude. Deathly, how's it going,
Okay.
man? uh,
All right.
do you want to just keep on learning linear, or just for the next week, just finish up chapter 3, or do you want us to add on 2 more chapters? Not two,
Oh, it's
add on to
whatever.
more chapters. Okay. I mean, whatever is your pace, but I think for next week, we're gonna finish up chapter 3, very quickly for next week, and then now we're gonna go for classification data, logistic regression,
Cool.
chapter 4, page 127. I will write the announcements in the Padlet link. And then I will also provide the corresponding link of the scikit-learn of the classification stuff, the logistic regression stuff. Logistic regression is actually kind of a hybrid of regression and classification, but yeah. All right, I think we're done for the week. All right, I'm gonna stop the live broadcast,
Okay.
but I kind of want your input afterwards. One sec, okay?
Sure.